Chapter 1.8.13 Security Checklist. This checklist provides basic guidance with links to more comprehensive documentation on various topics related to Kubernetes security. It is not exhaustive and is meant to evolve over time. The order of topics does not reflect priority, and some checklist items are detailed further in the text. It is important to note that using a checklist alone is not enough to ensure good security posture. Constant attention and improvement are necessary. Each category of checklist items should be evaluated based on specific security needs, as Kubernetes security is not one-size-fits-all. Authentication and authorization. After bootstrapping, the System Masters group is not used for user or component authentication. The Kube Controller Manager has the Use Service Account credentials enabled. The root certificate is protected either by an offline or managed online CA with access controls. Intermediate and leaf certificates expire within 3 years. Access reviews occur at least every 24 months. Role-based access control. Good practices are followed for authentication and authorization guidance. System Masters should only be used as a last resort, not as an admin user. Network security. The text discusses the importance of network policies and security measures within a Kubernetes cluster. It mentions that CNI plugins can be used to restrict network resources that pods can communicate with network policies being a common method for defining these rules. Default network policies are set to block all egress and ingress traffic within each namespace, adopting an allow list approach to ensure all workloads are accounted for. To enhance security, it is recommended to use a service mesh to encrypt all communications within the cluster if the chosen CNI plugin does not provide this feature. The text also highlights the need to secure access to critical components such as the Kubernetes API, Kubelet API, and etcd data store by not exposing them publicly on the internet. It is suggested to use mutual TLS, MTLS, for secure communication with ECD and restrict access to the Kubernetes API server to prevent exposure. Additionally, access to the Cloud Metadata API should be filtered to prevent potential information leaks, especially if using a cloud provider for hosting Kubernetes. Restrictions on load balancer and external IPs usage are also mentioned, with reference to specific vulnerabilities like CVE 2020-8554. Overall, the text emphasizes the importance of implementing proper security measures to protect the Kubernetes cluster from potential threats and vulnerabilities. Pod security. The text discusses the importance of implementing RBAC rights, pod security standards, memory and CPU limits, Seccomp, AppArmor, and SC Linux to enhance the security of workloads in a Kubernetes environment. RBAC rights allow for the creation, updating, patching, and deleting of workloads only when necessary. Pod security standards should be applied to all namespaces and enforced, ensuring that memory limits are set equal to or inferior to the request, and CPU limits may be applied to sensitive workloads. Seccomp, AppArmor, and CLinux should be enabled with appropriate profiles for programs, with Seccomp reducing the attack surface by restricting syscalls, and AppArmor and CLinux providing MAC and access control security policies. RBAC authorization is limited in granularity, with the only available granularity being API verbs on the resource itself. Pod security standards define 3 policies, privileged, baseline, and restricted, to limit how fields can be set in the pod spec for security. These standards can be enforced at the namespace level through pod security admission, which can operate in warn, audit, or enforce modes. Memory and CPU limits should be set to prevent DOS attacks, with caution against setting a memory limit superior to the request to avoid OOM issues. Seccomp can enhance security by restricting the calls a process can make, and profiles can be applied to pods and containers to reduce the syscall attack surface. Similarly, AppArmor and SE Linux can provide MAC and access control security policies, with AppArmor enforcing default profiles and SE Linux allowing labels to be assigned to containers or pods. Overall, by implementing these security measures, organizations can enhance the security of their Kubernetes workloads and reduce the risk of potential breaches or attacks. For more detailed information and tutorials on implementing these security measures, resources such as the Kubernetes Security Profiles Operator and specific blog posts can be referenced. Logs and auditing. Audit logs are secure from unauthorized access when enabled for use. Pod placement. Pod placement is important in managing the sensitivity of applications within a Kubernetes cluster. Sensitive applications are isolated on specific nodes or run with sandboxed runtimes to prevent unauthorized access. It is recommended to deploy pods of different sensitivity tiers on separate nodes to prevent potential security breaches. Node isolation helps prevent application container breakouts and unauthorized access to more sensitive applications. This separation can be enforced using features such as node selectors, pod toleration restriction, and runtime class. These features allow administrators to restrict where pods are deployed, which tolerations are permitted, and how container runtimes are configured to balance isolation and performance overhead within the cluster. Config maps are not appropriate for storing confidential data, while the secret API allows for encryption at rest. It is recommended to have a mechanism in place to inject secrets from third-party storage when needed. Service account tokens should only be mounted in pods that require them, and bound service account token volumes should be used instead of non-expiring tokens. Secrets necessary for pods should be stored in Kubernetes secrets rather than config maps. These secret resources stored in etcd should be encrypted at rest. Pods requiring secrets should have them automatically mounted through volumes, preferably in memory, using the emptydir.medium option. The secrets store CSI driver can be used to inject secrets from third-party storage. It is advisable to avoid granting pod service account RBAC access to secrets, and instead add secrets as environment variables or files. Service account tokens should not be mounted in pods that do not need them. An auto-mount service account token should be set to false to prevent this. Bound service accounts should be used for time-bound service account credentials in Kubernetes v1.22 and above. To ensure the security and efficiency of container images, it is important to minimize unnecessary content. Configuring container images to run as unprivileged users and referencing them with SHA-56 digests or validating their digital signatures at deploy time is crucial. Regular scanning of container images for vulnerabilities and patching known issues is also recommended. It is best practice for container images to contain only the essential components required to run the program they package, avoiding unnecessary utilities like shells or debugging tools. Using security context and the user instruction in Dockerfile can help ensure images start with an unprivileged user. It is advised to avoid using image tags, especially the latest tag, in favor of using complete SHA-256 digests for referencing images to prevent modifications. The use of image policy webhook can enforce this policy. Image scanning before deployment is essential to identify and prevent critical vulnerabilities. This scan should be part of the CI/CD pipeline to ensure only properly patched container images are deployed to production. Combining image scan results with compliance rules can help ensure the integrity and security of container images in production environments. Admission controllers. Admission controllers play a crucial role in improving the security of a cluster by enforcing policies and making additional authorization checks. However, it is important to properly secure these controllers, as they can present risks themselves. Several types of admission controllers are recommended to enhance the security posture of a cluster and application. The first group includes controllers enabled by default, such as certificate approval, certificate signing, and pod security, which restrict security contexts of deployed pods. The second group includes controllers like deny service external IPs and node restriction, which are not enabled by default but are recommended for enhancing security. Deny service external IPs mitigates against CVE 2020-8554, while node restriction restricts kubelet permissions to prevent unauthorized influence on pod placement. The third group includes plugins like Always Pull Images and Image Policy Webhook, which are not enabled by default but can be considered for certain use cases. Overall, the appropriate selection and configuration of admission controllers can significantly enhance the security of a cluster and application.